Welcome to the 2016 NASA Ames Summer Series. Humans are evolutionary successful species due to our inherent drive to explore and migrate. This, in part, is due to our ability to invent tools and adapt them for the purpose of surviving new environments. Today's talk, entitled Planetary Exploration Reinvented, will be given by Dr. Terry Fong. He received a bachelor's in science in aeronautics and astronautics from MIT, and then followed with an MS in aeronautics and astronautics, also at MIT. He then came to Ames from 1991 to 1994 and decided to go and do a PhD. So he went and started a PhD and received a PhD in computer science from Carnegie Mellon University. During that time, he also co-founded a company, Fourth Planet, producer of interactive tools for real-time information visualization. In 2004, he came back to Ames. So all of you that are here for the first time, maybe we'll see most of you back here. He has numerous publications and awards. Please join me in welcoming Dr. Terry Fong.
Thanks very much, Jacob. Good morning. It still is morning, I think. I'm really glad to see so many people here. Quick show of hands. How many of you are here just for the summer, at least for now? Wow, so that's almost all of you. So that's great. That means I can go rag on all the people who are here all the time who didn't come to see me, although they were encouraged to. Let's see, as Jessica said, there will be some questions at the end, but because you get to grill me at the end, I'm going to start off by grilling all of you to start with. So, quick show of hands, how many of you were born after December 1972? Wow, almost all of you again. Can any of you tell me why December 1972, and specifically December 7, 1972, is important? Not yet? Well, so stay tuned. I'm not going to answer that right away, but just keep it in mind. Next question. How many of you work in planetary exploration or space sciences? So only a few. So hopefully that means a lot of what I'm going to tell you will be new to you, and you won't just go to sleep and then come apologize afterwards. So let me tell you what I'm going to describe today is some of the work we've been doing here at NASA Ames for the past decade in my group, the Intelligent Robotics group, to try to come up with new tools, new techniques, new ways of doing planetary exploration. A lot of what we care about at NASA across the board, of course, is learning more about the universe, learning more about the solar system, understanding differences of the moon, Mars, and other places compared to the Earth. And doing so really helps us better understand how we all came to be here, and to also think about the future of how we can perhaps expand human presence from where we are today to where we would like to be in the future. So maybe what I'll start with is trying to answer the question I just asked you about why December 1972 is so important. And the reason is that was the very last time that humans went beyond low Earth orbit. That was, and still is today, the state of the art of human planetary exploration. December 1972 is when Apollo 17 went to the moon. And in particular, this image, to me, it really sort of summarizes where we are still coming up on 44 years later in terms of the state-of-the-art of human planetary exploration. This is a picture of Jack Schmitt, astronaut, geologist on the surface of the moon, with his car, the Lunar roving vehicle, doing field work with handheld tools, shovels, sample collection bags, walking inside of a pressure suit on the surface of the moon. And if you think about it, that's both really exciting, the fact that we did get out beyond low Earth orbit, that there was exploration of the surface of the moon. At the same time, it's a little sad if you think about it, that was 44 years ago. And a lot has changed since then, which means that part of the question is, well, can we do things differently? Can we do things better? Or perhaps are there other ways to think about planetary exploration? In particular, a lot has evolved over the past 40-some years in terms of our ability to use tools, especially things like orbiters. You see on the top row there are a number of different satellite systems that have been back to the moon. The Japanese, the Indians, NASA have sent probes to orbit the moon, collect high-resolution images, and to use other instruments to measure the properties of the lunar surface. We've learned how to live and work in space. The space station's been up there for more than a decade now, where people routinely conduct experiments. They do work on board space station. They learn a lot about what it's like to live and work in a really unnatural environment for humans. And of course, NASA has been very fortunate over the past few decades to be able to send our robotic explorers far beyond Earth orbit. We've sent landers such as Phoenix to Mars. We've used Mars rovers to explore the surface of the fourth planet. And over the past few years, we've been doing a lot of experimentation on space station with robots like Robonaut 2, as well as here on Earth with a variety of robots to understand how robots can be used productively for planetary exploration. But if we look at where NASA is headed, we're trying to embark upon a journey to Mars. We're trying to go from where we are today, which is a lot of work on the Earth or in Earth orbit, to a future where we do have humans on the moon again, at Mars, in Mars orbit, on the surface of Mars. And being able to carry out these missions requires us to do a lot of development, a lot of thinking of how do we really make that possible. These missions, as we're looking to go further and further away from Earth, are more complex. They are longer duration. They require new technology. They require new tools. A variety of different things we have to worry about include robotics, deep space habitation, spacesuits, communications, propulsion, lots of different things that we today still don't quite have all the answers. And so one of the challenges for all of you, if you're interested, is to try to help NASA answer some of the questions of how do you create the tools and the techniques, the methods that we need for doing future exploration, at least future human exploration of deep space. So what I'm going to talk to you about today are three of the things that we've been doing here at NASA Ames in my group to really try to expand and try to reinvent in some way the way that planetary exploration can be conceived of, can be performed. 3 parts, so a 3-part act today. The first one in terms of robots for human exploration. How can we use robots to improve the way that humans live and work in space? Number 2 is an interesting area called neogeography. There's been a real revolution in the past couple of decades of how we think about using maps and images and combining maps and images together. So I'll talk a little bit about that. And the third is in terms of exploration ground data system, which is a fancy way of saying how do you organize the information that you're using to plan and carry out exploration missions through software in particular. Do you do that on a laptop? Is it on a tablet? Is it with a giant ground control team like we've routinely done here at NASA? So we'll go into each of these in a little bit, and hopefully this will give you some insight of some of the different ways to perhaps explore in the future. So we'll start off with the robots for human exploration. This is a topic that's been near and dear to my heart for many years now. And the reason that it's really, I think, interesting is this whole notion of how you combine humans and robots together into an effective team. NASA has had a long history of using robots for deep space exploration. We've had a long history, although some of it is quite historical now, of using humans to do exploration in space. But the question looking forward is how do you combine humans and robots together? Are there effective ways to create teams, robots that can complement and supplement the activities of humans? And how do you do that? So one of the things that we've been doing here at Ames is trying to look at the whole trade space. How do you combine humans and robots in an effective manner? And I like to point out to people that human-robot teaming is not just what you might see in the movies. It's not just Luke Skywalker and R2-D2 just being closely walking hand in hand or hand in gripper or whatever. But it's a broader set of configurations. It's the idea that you can have robots working before humans, or robots working in parallel or supporting humans, and of course robots working afterwards. So the whole notion of before, in parallel or supporting, and after is an interesting twist on the idea of human-robot teaming. It's not just about hand-in-hand, it's really the whole idea of looking at how they can be complementary over a broad range of space and time. And not going off to lunch, let me go back up here. So one of the things that we did a few years ago was conduct an experiment called the Robotic Recon experiment. This was an experiment that we ran to understand a little bit better how having robots working ahead of humans might really improve the overall productivity of the exploration, make it more productive, make it more effective. To do this, we set up an experiment where we tested exploration of an unknown area. I'll get into the details in a minute here, both with and without the benefit of having robots working in advance. And we tried to use this experiment to better understand what are the requirements, the kinds of things that are needed to carry out this kind of joint human and robot activity in terms of the instrumentation the robots have to carry, the communications, the navigation, the planning. How do we understand the coordination between robot activity and human activity? All these kinds of questions are things that we tried to look at. And if any of you are really interested in the detailed results, there's a nice paper that my deputy wrote, Maria Willett, published back in 2011. I'm happy to give you the reference afterwards, or you can look at it on YouTube, so you don't have to try to scribble it down right now. But to motivate this, let me tell you a little bit about why recon or scouting in general is useful. And to do that, I'm going to tell you a little bit about Apollo 17. As I mentioned, Apollo 17 happened in December 1972. It was the last Apollo mission, and it was the only mission where one of the astronauts was a trained scientist. Jack Schmitt, geologist by training, was kind of a last-minute replacement, but he was a member of the crew who had training, a background in field geology. That is, he was used to going out and doing field work, walking around, trying to understand multiple hypotheses at the time about the way that the environment was constructed. What are the different geologic units? How do they fit together? Where do they come from? And one of the things that Jack did was he was part of a number of sorties, a number of EVA activities on the surface of the moon. The second of those, EVA-2, started off from the landing site, and they went out along, you can follow the blue lines, towards the South Massif, and then they worked their way back out on the upper part there to what was termed Station 4. It's a location called Shorty Crater. You can see by the map here, it's about 3/4 of the way through the sortie, about 75% of the time through. And at that location, Jack Schmitt, walking around, trained field geologist, discovered orange soil. Actually turns out to be this pyroclastic material. You can see here there's this volcanic material in orange. It was really exciting. It was perhaps the most exciting discovery of Apollo 17. But it happened 3/4 of the way through this traverse. And as you can imagine, they were running short on time. They were running short on oxygen. They couldn't stay there very long. And so they quickly grabbed some samples, and they went back. And you think about it, perhaps the most important scientific discovery of Apollo 17, and you didn't really have a whole lot of time to study it. So you think about how could you perhaps do better than that? And of course, the obvious answer is, well, if we had known that Shorty Crater was an important place, maybe we would have gone there first, or maybe we would have sped up the traverse so we could spend more time there. But the only way you can do that is by having better information. So you need to do scouting, you need to do recon to make that determination. So for us, it was an interesting question. Okay, so if we want to think about reimagining Apollo 17, how do we do this? And how would you carry this out by using a robot? That was the background for this experiment we did back in 2009, where we went through a sequence of steps. We did a pre-recon sort of planning phase for this combination robot followed by human mission. The first phase in terms of pre-recon looked at using satellite images. We did some planning with a geologic map we developed to try to lay out where we would want to do scouting ahead of time. Scouting carried out by a planetary rover. In the second phase, and what you see here is the K-10 planetary rover, under control by a ground control team, followed up by some secondary planning with for a human mission, and then ultimately carried out as a simulated astronaut mission. This is an experiment that we carried out over the course of a number of months in 2009. We did this at a place called Black Point Lava Flow. How many of you have ever heard of Black Point Lava Flow? Say one, maybe two people, three people. So Black Point Lava Flow is 65 kilometers north of Flagstaff. It's in Arizona. It's what we consider to be a planetary analog, that it has some characteristics that are similar, in this case, to a feature on the moon called the Straight Wall. It's a large lava flow, a fairly old lava flow. It's basaltic, volcanic rocks, a lot of different geologic units, that is different areas that have very different characteristics. And we were interested in studying this because it was a very large structure, 15 kilometers wide, east to west, about 5 kilometers north to south, a large area to cover if you're going to try to do exploration in the style that was done during Apollo, which I said is still the state of the art today for human exploration.
2 NASA robots are exploring the dusty and rocky terrain of Arizona desert to simulate a scouting mission on the moon. The robots, known as K-10 Black and K-10 Red, are using their onboard cameras and 3D laser scanners to take images and map the terrain.
We're looking at using a smaller robot like K-10 to explore the area ahead of time to make the astronauts' time more efficient on the moon.
The data is transmitted to mission managers at the Ames Research Center, where the robots are remotely controlled. Robotic scouting missions to the moon will provide astronauts a lunar roadmap that will improve the quality and amount of science data collected during their stay on the lunar surface. Information gathered from the K-10s will be used to plan a simulated astronaut mission to the moon this August. And that's this week at NASA.
Or at least that was This Week at NASA back in 2009. The video is interesting in a couple of respects. One is you saw a planetary rover that was being interactively controlled by a science operation team. They were using a number of instruments on board the robot, cameras, 3D scanning, LiDAR, to better understand the environment. But the primary purpose, of course, was not moving the robot from point A to point B. I mean, that's a sort of a secondary effect. Roboticists or operators care about, making sure the robot is safe. But the primary purpose was, of course, to use the robot to gather information that's necessary for improving the planning of what comes next, which is the human mission. And so one of the key questions was, how should you carry out that mission? What sort of data should you collect? Scouting is a non-trivial thing. The goal is not to go out there and spend every possible hour doing a super detailed, comprehensive study of environment, because you just never have the time. In fact, you don't have the resources either. And so the question is, how can you be smart about going to different locations to gather the most important information that will be useful for planning what comes next? One of the things we did, of course, was we used a number of different instruments on that robot. As I said, it had laser scanners, it has cameras. We also happen to have a panoramic imager called GigaPan, which allowed us to create very high-resolution panoramas. And we collected a lot of recon data, 8.5 gigabytes of data over 52 hours of remote operations. And you can see here it was spread out over a fairly large area. We had an area to the west in blue there, and an area to what we consider to be the north section, and a fairly large amount of data collected in the center here. A lot of data. This data was important because it really helped complement some of the data that we started out with. As I told you earlier, we began this whole experiment by starting off with satellite imagery, the kind of imagery we would get today if we were to go back to the moon or go to Mars. This is an example of orbital data. This comes from Digital Globe. It was a QuickBird image at the time, 60 centimeters per pixel. You can do better than that today. But it's a commercially available, state-of-the-art orbital image. And if I tell you a little bit more about this image, such as, well, here's the location and here's the time of day, and you do a little bit of math based on where the sun was, you could probably look at this area highlighted in red and figure out, oh, this area where you see some dark area, this kind of dark shadow, is actually a cast shadow. You could infer that on the bottom of the image, that section of the ground is higher than what's inside the box, and so the shadow is cast that's falling into that area. And so what you're really looking at here is not an area that has different colored materials, but rather is a basin where something is lower. That's the kind of thing that you can glean from this image. And of course, that might help you in terms of planning for navigation, because well, I don't want to start on the bottom edge and just drive straight because I'll probably fall off of a cliff. But it doesn't tell you more than that. It doesn't tell you in particular, why are there some differences in there, and why is that area, which kind of looks a little bit like I guess North America, in white. What is that? Why is it so white? How's that different from this very, very deep black area? And if in fact that black area is shadow, what's in there? And so one of the frustrations we have of using even this high resolution satellite imaging is that it doesn't give us enough information to really plan surface activities. Well, contrast this kind of data, which comes from satellites from orbit, with this kind of data. which is what we gathered with our robot. This is information gathered with imagers. We have, for example, this top panorama inside that exact same area, the same basin. And now you can see, well, yes, it is a wall, so we definitely do not want to drive off of that. But more interesting, of course, is you can zoom in and take a look at, from an oblique angle and understand, well, in this case, the wall looks like this. We could look down close to the ground in very high resolution, because here, of course, you can have high resolution imaging on the surface and determine whether or not it's important to go to this area or if it's just a feature to avoid. The other interesting thing, of course, is that if you do have these sensors that are on the surface, you can have very close-up, very extremely high-resolution detailed measurements that are just impossible to acquire from orbit. This is an example of a camera image that we also managed to image with our 3D scanning laser system here. Very high resolution, 3 millimeter depth resolution, the kind of information that makes it really, I think, effective if you're trying to plan whether or not you should go to an area, collect samples, or merely take a look at it from a distance. What we did after that robotic mission, of course, is we took a look at how we could use that information and plan a follow-up human mission. The mission that we carried out at that time was done with some of our friends at NASA Johnson, who back in the 2009 period were developing a vehicle called the Space Exploration Vehicle. This is meant to be, the far descendant of the Lunar roving vehicle that I started off with, talking about from Apollo 17. In this case here, it's a vehicle where the idea is that you keep the spacesuits outside of the vehicle. You can see in the bottom image there, these spacesuits that are mounted through a mechanism we call a suit port. And so the astronauts would live inside this vehicle in a nice shirt sleeve, clean environment. When they needed to go outside and do field work, they would step into the spacesuits and detach and be able to then work outside the vehicle. This helps minimize the amount of dust and other materials that you might bring in and contaminate the clean living environment. It also allows us to be very efficient at being able to quickly go in and out of a place which is comfortable for living to have to go work on the outside, rather than go through a very long process and airlocks and all these kinds of things. What we did during our experiment was we divided up a set of astronauts, or at least simulated astronauts here. I shouldn't say simulated, because actually two of our test subjects, Mike Gernhardt and Andy Thomas, are in fact astronauts that have been on the space station. We combined them along with Brent Geary and Jake Bleacher, who are field geologists, practicing geologists that work for NASA. They routinely go out and do field work. And we had them carry out a number of different traverses to do sampling, do field work. And what we did, of course, is we took the data from the robotic recon mission that we had carried out ahead of time, and we used that information, and we gave that information only to one of the crews. And the other crew, we said, well, we're going to try to pretend like you're just Apollo. You only have the benefit of satellite imaging, orbital data, and then we'll see what are the effects of working with and without surface information. So here's a short video just to give you an idea of what the space exploration vehicle looks like. Large six-wheeled vehicle. You can see here the astronauts are now into their simulated spacesuits, and they're going out to do field work. What was interesting, of course, is that our focus was on using robots. We didn't try to optimize the use of hand tools, and so the tools that they used were very similar to what was used back during Apollo 17. This idea of using shovels and collection bags to collect samples. Let's go ahead. In the interest of time, we'll move on here. Some of the results that we got from this study is that in the area, the western area, the pre-recon plan that was designed, and again, this is based purely on satellite information, was designed to be very Apollo-like. That is, if you think of what was done during Apollo, they tried to do very rapid area coverage. Because you only had a single visit, you had to try to maximize the area covered, trying to visit as many different geologic units as possible because you don't have a chance to go back there. What we found, of course, is that, and maybe this is all common sense, is that with the benefit of surface recon information, our plan was significantly different because we decided that, the things which look radically different from orbit, the things which appeared to be, incredibly important to go look at this unit versus another, turns out, well, actually they're very similar on the ground, so we don't really need to do that. And as a result, our pre-recon plan and our post-recon plan are significantly different. So one of the impacts of having scouting information is that we were able to really improve the prioritization and the targeting of the work being done by humans. It seems fairly self-evident. The more information you have, the better. But other interesting results were that, well, just having information is not enough, because part of the question is how do you coordinate the activities done by humans versus robots? I mean, if you're going to send a robot out for scouting in advance, where do you go? How do you carry out that scouting? And then how do you take that information and then pass it over to humans? Do you provide humans, for example, with the data that was collected by the robots? Because, of course, the robots are going to locations that maybe you're not going to send humans. Is that helpful or not? It was a really interesting experiment because it really started opening our eyes to this whole notion of coordination between humans and robots. Something that was not really evident to us was a key driver, but turns out to be extremely important. So that was the robotic recon experiment. After we finished that one, of course, we were sitting around thinking, well, what's a natural follow-up? And someone in my group said, well, we should just write a proposal to do the opposite. We should go write a robotic follow-up experiment. And so we did. And it's, of course, a nice thing to do if you're out there writing grants. You do some work, and then your second grant, you just take what you just did, and you flip it on its head, and you can go get some more funding to do that. So we did another experiment called the robotic follow-up experiment. And this was meant to look at solving the problem that we have when we're out doing field work, and that we never, ever have enough time. If you're in the field, oftentimes you run out of resources, or your field experiment just runs short. And you get back home and you think, boy, if I had only had more time, I could have done more observations, I've collected more samples, I could have done additional work. Now that I'm sitting at home, sitting in my office, boy, if I'd just gone to this location. But you can't. And so one question was, well, what if you combine human activity with robots and you leave the robots behind so that after you get home, you can actually use the robots to follow up and do the things that you would have liked to have done if you could have stayed in the field longer. Now, of course, why is follow-up useful? I'll show you this slide, and you probably recognize this since I showed it a few minutes ago, except before it said, why is recon useful? Apollo 17, same sort of problem. As you recall, out here at Shorty Crater, not enough time to really collect all the samples you want, not enough time to do all the detailed field work. Well, what if you had left the lunar roving vehicle behind, but it was a self-driving car today, and it could carry out its own set of activities? Well, that's fine. Humans can go home, leave the robots behind, and then you could use those robots to do some detailed, systematic work afterwards. It was an interesting idea, something which I fully believe is likely to happen in the future, because these days when we build things, they all have software in them, whether it's a tool or a vehicle or a robot. It's very likely in the future that as humans go to planetary environments, whether that's the moon or Mars, they're going to leave things behind. And then afterwards, we're going to operate them robotically. So to try to understand what are the benefits of this, we went out to a different analog site. This was a place in the Canadian Arctic called Haughton Crater. Haughton Crater is about 74 degrees north. It's in the high Canadian Arctic. And here's a bit of trivia knowledge for all of you. What's the largest uninhabited island on Earth? And the answer is Devon Island, which is where Haughton Crater is located. If anybody asks you, where should you go to get away from everybody, this is a great place for that. Devon Island is an interesting place because it's snowbound most of the year. There's about a 6-week period in the summer where the snow's all gone, at least on the surface. There is permafrost, a lot of interesting subsurface features that persist year-round because of the very cold, arid climate. And we went there because Haughton Crater, this is a picture of it here in the far north here, is an analog for one of the most interesting places on the moon called Shackleton Crater. They're both polar impact structures, about 20 kilometers in diameter. Haughton Crater has subsurface water ice. Shackleton Crater, we believe in many places, has subsurface water ice as well. They're remote, isolated, difficult to access. Interesting location for us to go try to do some experimentation. And so what we did back in 2009 is we carried out a crew mission by first having humans go explore very much in Apollo style. They used this Humvee as a proxy for a future vehicle. And they carried out a couple different surveys. One in terms of geologic mapping, which is a classical way that field geologists go out to try to document the history of an area, trying to examine the structural geometry, the major units of an area. And the second was a geophysical survey using handheld, or at least hand-deployed, ground-penetrating radar to examine the 3D subsurface structure. Here are some example images. These were collected by Mark Helper, one of our field geologists who we sent up to Haughton crater. He collected these images with a handheld camera and identified afterwards different contacts between different carbonates. You can see a variety of different sediments and different views of the Haughton impact structure. Here are some examples of the ground penetrating radar data. This was collected by Assam Hegi, who at the time worked at JPL. And what he was able to identify is the presence of subsurface ice wedges, locations where the ice in the subsurface is pushing up in little peaks towards the surface. Based on that, we then sat down and said, well, how can we follow up with this with a robot? Where should we send robots to do additional work, complementary work to what was done by our humans? And we decided to create a number of different plans in these various sites. Some of these are traverses, where you're going from point to point to point. Others are systematic surveys, where you might be following a raster or lawnmower kind of pattern to get detailed information about that site. And here's an image, a movie of one of our rovers. This is the K10 rover that we sent to Haughton crater. It turns out it was the same rover that was in Black Point lava flow in Arizona as well, but this time we added some different instrumentation. On the bottom of the chassis, there's a ground penetrating radar. This was meant to complement the work that was done with the handheld tool. There's also an XRF device on the back. There's a high resolution 3D scanning LiDAR on the top. This is a robotic a gigapan system that we're using for panoramic imaging. And we use these to conduct the follow-up work. Now, one of the interesting things about this, of course, is that we were trying to understand the impact of using robots. So we didn't want to just have the robots replace humans. We wanted to try to understand how the robots could function in ways that are complementary. So this robot, for example, is very autonomous. It's able to drive and navigate from point to point by itself. All the steering of the wheels you're seeing here are being done fully autonomously by the robot. It's making its own decisions of how to drive, which places to avoid, when to acquire images based on high-level guidance provided by the planning team. Some of the results from this is that we found that using robots in sort of a follow-up mode was very useful because you could verify and amend the data that was collected by humans. In some places, you were able to go back and confirm some of the hypotheses that the human team had when they were carrying out the work by themselves. And in particular, in terms of the Geophysical Survey, we were able to correlate in a very high-resolution way surface and subsurface features, because the robots were able to acquire a lot more detailed information in a very precise manner. Robots, of course, are very, very easy to track. We use positioning systems. We know exactly where they were. A bit harder to do that with humans. However, we learned a number of interesting things. One is that it's really non-trivial trying to plan the coordination between human activity and robot activity. If you send humans out and tell them, well, a robot's going to come along afterwards, it's really hard for those humans to think, well, can the robot actually come here or go to that location that's far away that I'd like to send it? Because one of the problems that we have as humans is it's difficult for us to understand in detail what are the performance limits, what are the capabilities of those robots. Can we make them go to the place where we really want to? But that's an important thing because, of course, if you're depending upon somebody else, whether it's a human teammate or a robot to follow up after you, you need to understand what their capabilities are. And you have to take that into consideration when you're planning, because otherwise, when you hand off a plan and say, hey, go do this, at the end of the day, you're not going to get the results that you wanted. So one of the things that we learned from this work of having robots working before and after is that it's really critically important to think about human-robot teaming and thinking about what that means. Coordination is clearly important. Understanding the capabilities of each, whether the human or the robot, is important. Understanding, how do you transfer information? The way that humans acquire data with our senses and interpret that is very, very different than the way that robots do that. These are the kind of issues that I think are critically important if we really want to depend upon robots for future planetary exploration when they're working before or in support or after human teammates. any case, that was part one, talking about robots for human exploration. I think when we get to the end of this talk, if any of you have questions about that, please keep in mind this whole idea of robots before and parallel and after. It's a really interesting area, and I think that's fundamentally something that's going to help reinvent the way that humans explore planets. But let me switch now and talk about a different set of tools, another way of thinking of how can we change the way that we're doing planetary exploration. And that's in terms of a whole domain that's over the past decade been called neogeography, or sort of reinvention of the way that we think about the use of maps. How many of you in the past, say, 6 months or so has relied upon a digital map, Google Maps or Bing or what's on your phone? I think it's like every single person in this room. Now, what's fascinating is if you go back and you ask, like your parents, your grandparents, that same question, the answer will probably be, no, we didn't do that, or at best, we used a paper map. Some of you are old enough, I'm going to date myself now, to know what a triptych is. This is a thing that came from the AAA. People are like, AAA? What's the AAA? Well, that's a whole other question or topic of discussion. But the point is that over the past decade, we've come to rely increasingly upon the use of geographic information systems that are online, that are real-time, that have a lot to do with mapping. And so what's important for us here at NASA is to understand how can we do the same for planetary exploration. I mean, here on Earth, we really have gleaned a lot of benefits from the existence of GPS and satellite data and online maps. How can we do the same for planetary exploration? Well, probably doesn't surprise you that over the past few decades, NASA and other space agencies have gotten increasingly good at acquiring high-resolution data from orbit. As I mentioned for the moon, we've had a lot of orbiters acquire information over the past several years. And the question is then, based on that information, how can you use that to improve the way that you carry out scientific investigation? How do you use that to improve the way that you plan future exploration missions, whether those are orbital missions or ones on the surface? I think one of the reasons why this is important is that we have found ways of acquiring more and more planetary data. And at the same time, it's not just an exciting thing, it's also a real problem. Over the past few decades, the number of images of the moon and Mars has grown at greater than exponential rate. In terms of the amount of data that we acquire, we are really great at getting that information. What we're not so great at is being able to find ways of processing and using that information, because we have a lot of data. And it's not just the number of images acquired, it has to do with the size and scale of these images. We have really, really big images these days. Images, for example, from the Mars camera called HiRISE, which is carried by the Mars Reconnaissance Orbiter. 20K by 40K images are routine. These are huge pieces of data. And if you think about it, trying to process these in a manual manner, the way that we've done for many decades, the way that's traditional in the space science world, which is human-intensive cartography, is really, really limiting. There's only so much that humans can do, no matter how many humans you might have, because really there aren't that many skilled cartographers in the world, to be able to process this data. And so the question is, how can you make use of this in a faster way? Well, one way of doing that is doing automated stereo processing. We can use computer systems to take pairs of images, and we can reconstruct 3D terrain by processing these. NASA has done this for a long time, although traditionally with manual tools. We can now apply computer software to do the same sort of thing. Here in my group, we've developed a map processing pipeline that takes data from lots of different sources, runs it through a variety of computer vision algorithms that we may run on, say, the supercomputer here, and output that in different ways. We've created lots of models of Mars. We've worked with a number of different imagers. We've done the same thing of the moon, and some of the work we've done is actually with historic data, where we've taken scans of the original Apollo films from the Apollo panoramic and metric camera and created these high-resolution 3D models. We've used that to create these high-resolution 3D maps of the moon. For example, we've created a digital elevation map, a 3D terrain model of a large mosaic of 4,000 images that have been all registered and adjusted together. And then, of course, you can reconstruct this and project this back out to the moon. And the reason why this is exciting is that once you have this data in digital format, is you can not only process it, but then you can visualize it in ways that are really different. One of the great tools that was created over the past decade was a tool called Google Earth. I'm sure most of you have probably played with it at some point in your life. I'm not sure how many of you are aware that Google Earth actually has a Mars mode and a Moon mode. If you go back to your desktop computer or your laptop and you launch it after this talk, click on the toolbar. There's a little Saturn icon. And if you click on the Saturn icon, you can flip to these other modes, and you can find data that we created and then worked with Google to push out to the broad public, both Mars and the Moon.
Switch from Earth to the Moon in Google Earth. Go to the top toolbar and select Moon. Now you'll be able to explore the Moon and Moon-related content in the left panel layers. With historical charts, you can explore actual planning charts of the Moon from the Apollo missions. These high-resolution maps were used for astronaut training and by mission control during the lunar missions. Clicking the Human Artifacts layer displays those objects humans have left on the Moon, including 3D models of spacecraft. In the left panel, you'll see links to the 6 Apollo landing sites on the Moon. Double-click Apollo 11 and zoom in and see it in more detail. Once you arrive, you can watch video clips of Neil Armstrong's first steps on the Moon and many other significant mission moments. View 3D models of mission spacecraft like the Apollo 11 lunar module, Eagle. And see panoramic imagery taken by the astronauts themselves of the Moon's surface.
Let me flip over and show you one of the other interesting things that's embedded within Moon and Mars and Google Earth, and that is guided tours. So if you want to go and explore the Moon, you don't have to just look at it by navigating yourself, but you can actually take a tour with, for example, Jack Schmidt.
I'm Jack Schmidt, Apollo 17 astronaut and geologist. Flew on the Apollo 17 mission in December of 1972. The crew of Apollo 17 was an aggregate of 2 backup crews, Apollo 14 and 15. I replaced Joe Engle on that crew, and Gene Cernan would be the commander, and Ron Evans was going to continue as the command module pilot. Gene Cernan got out of the spacecraft first, and I followed him fairly quickly afterwards. We were in a valley deeper than the Grand Canyon of the Colorado. The mountains on either side were 2,100 meters, or about 7,000 feet high. The sun was as brilliant as any sun that you can imagine. Even more impressive was the Earth, which was hanging over one of the mountains and stayed hanging over that mountain, the South Massif. And that was really a magnificent sight for me, and that's what I remember as being sort of my first real impressions of the Valley of Taurus-Littrow.
So the interesting thing, of course, is the fact that we have these tools now that allow anyone, not just a trained planetary scientist, not just someone who works at NASA or another space agency, but anyone, you, your best friend, your grandmother, to go explore these other environments, these different planets. We've also done some work not just with Google, but with Microsoft. Microsoft had another piece of software called Worldwide Telescope that we worked to help add planetary data to.
A couple years ago, in working with Chris Kemp from NASA, we started thinking how we could bring together the features and the functionality that we had in Worldwide Telescope to some of the planetary data sets. And we really wanted to focus on a unique asset, the high-rise imagery that Mars had. And so we started working and collaborating to figure out how we could bring to the public and get it in their hands. The high-rise imagery is a one-of-a-kind camera that's on board one of the satellites that goes around Mars and takes really high-resolution images of the planet's surface.
We have complete base maps of Mars as well as very high-resolution data that are actually higher resolution than most of the satellite data that is publicly available of Earth. And so we can actually see Mars in better detail in some areas than we can see Earth.
This project leverages several teams within NASA and then also, of course, teams at Microsoft. And really, it's bringing together some of the kind of cutting-edge technologies in both institutions to do something which has not been possible before.
People can go for a walk on Mars now and actually see the craters, see the cliffs, and get appreciation of the scale in a way that they could never have done before.
Mars is a big place. By making this raw data, this full high-resolution data available in a worldwide telescope, we're just going to open all of that up to classrooms across America, across the world, and connect with the public in a way we've never been able to before. So if we can really put projects like Worldwide Telescope in data sets like the Mars HiRISE data set, I think we could inspire the next generation of Americans, like Apollo inspired this generation of Americans, to really be innovators, be thought leaders, and be leaders in the world.
In the interest of time, I'm going to skip ahead and just take us to the last bit I want to tell you about, which is Exploration Ground Data System. You all know, you've probably seen on TV that when NASA operates missions, we typically have large control rooms of very excited people trying to figure out how do we operate a robot or a spacecraft, how do we work with humans on the space station. These are large teams. And one of the key questions is how do you coordinate the activity of those teams on the ground supporting those things which are not on the ground. Things are in space, things are on other planets. Traditionally, we spend a lot of time creating one-off systems. That is, we'll create a mission and we'll staff up a whole team and build a very expensive, very large software system that's used just for that single mission. And that's been an effective way for us because we don't have that many missions. I mean, there are frankly a number of missions out there that take decades or maybe a whole career to put together. But if you think about it, the world doesn't operate that way anymore. Software is something that changes very rapidly, whether it's on your phone, on your desktop, your laptop. It's something which is distributed. We don't have large systems in our offices. In fact, most of us may not even use an office. We may exist by working in cafes. And so the question is, how do we try to catch up in terms of the world of software for the way that we operate these missions? So here we've been trying to figure out how to create web-based systems to help plan, monitor, and ultimately explore whether we're using robots or humans to carry out activities. And this, of course, as I was saying just with the robots before, is the kind of thing that can be done before, so in a planning phase, during the mission, and when you're carrying something out, human or robot, and afterwards, the idea that you can use the same sort of software to support your analysis. We've been looking at a number of different exploration missions, at least future mission concepts, some of those involving humans in, say, the Space Exploration Vehicle in the center there, some using robots, as you've seen before with the K-10 planetary rovers, and other cases that we've tested out over the past several years. NASA carries out, pretty much a yearly basis, a number of different of these planetary analog field campaigns. We tried to support these. In fact, there's one that just wrapped up last week that was at the Crater of the Moons in Idaho, where we were trying to use our software to support exploration. The system we've developed here in my group is called the Exploration Ground Data System, and like all good NASA projects, has a nice acronym, XGDS, which is only meaningful to the developers. But XGDS is a system, it's a web-based system that allows us to combine these maps and data, like I just showed you in the previous segment here, in a way that allows people to interactively browse without a whole lot of training and be able to use that to carry out these exploration missions. For those of you who are the geeks in the room and really want to know about the details underneath it, it's a web-based system. It uses Django and MySQL, pulls together a lot of different kind of data interfaces, different user interfaces, including Google Earth, OpenStreetMap, web browsers, and all kinds of data. If you're interested, I can point you to a couple papers about this, or if you're interested in coming to work on this, come see me afterwards and we can talk about that. But what we use this tool for is to have a nice way to quickly and rapidly and flexibly support different people who care about science operations for field exploration missions. We serve maps, we serve data that we use for planning purposes, for laying out traverses. We can track in real time people and robots as they are acquiring data. We can represent the data products that are acquired, either real live raw data or the derived products after processing. We can show raster plots, so you can actually look at signals over time, information that's very important if you're trying to look at time variant signals or things which are really driven by where you are at a certain moment. We can turn that information into raster maps and show a different coloring of how various parameters of the environment, various characteristics change over spatial regions. We can log different information in real time. So this is sort of like a stenographer function where you're trying to log information, and we can cross-link those with images and geographic data. And of course, then you can take all the information and provide tools to help people browse this information. These are the kinds of flexible tools that we all are used to today in our everyday life, but which we've never had before in terms of real-time mission operations, especially for exploration missions. We've done this work in a number of different projects. One of those is the Pavillion Lake Research Project. It's an interesting project that's led by Darlene Lim here at NASA Ames, where they've used these one-man submersibles to map out microbial light formations in a lake a bit north of Vancouver in Canada. This is actually a video of Darlene having a fun day at work where she's out doing some exploration in this one-man submersible. These are the kind of images that are collected by the pilots as they're flying around underwater in Pavillion Lake here, and they're making real-time observations, commentary that is streamed up along with this high-definition video that we're recording, and then putting into our exploration ground data system in an effort to try to understand the formation of these really interesting areas within Pavillion Lake. We've used all the information, put it together into these different tools, and that's really helped us figure out how we can better support distributed science operations as we're looking for future missions. The kind of thing that we feel is important to be more flexible, more extensible, and ultimately more reusable if we're going to carry out missions that are not just one-offs, and missions that are not just one per career, but missions that happen routinely throughout the lives of the people involved. I'm just going to wrap up right now since I see that we're running a little bit short of time here, and just point out to you that I've told you about 3 different ways of perhaps reinventing planetary exploration. The idea of using robots with human explorers, robots that work before, in parallel, or after. Very important, interesting challenges in terms of how do you coordinate human and robot activity. Secondly, in the fact that today the world relies upon geography in ways that we never thought were going to be critical to our everyday lives, but fundamentally are also important, I think, for planetary exploration. And finally, this whole notion that it's important to think about how we reinvent software to make it more flexible, more distributed, more web-based, lighter weight, to really support the way that we can carry out exploration tasks. But in essence, all that's really just meant to be a starting point for trying to reinvent the way that we explore outer space. It's something that I would challenge all of you, each and every one of you, to think about. How can we take the tools today and make them better? How can we create new tools and go further than we've ever gone before? But with that, I'll wrap up and turn it back over to Jacob.
Thank you very much. Very good. So we have time for a few questions. If you have a question, please raise your hand, wait for the microphone, and ask one question only. Thank you.
Hi there, thanks for the amazing talk. Can you actually say any kind of main differences for a combined mission robotic human between the moon and Mars?
So I think that one of the things that NASA cares about today is understanding how do we get to Mars. The agency is focused really on this whole journey to Mars, and that involves the development of tools and systems that can be tested out on the moon and used ultimately on Mars. And one of the areas that the agency really is putting a lot of effort into right now is understanding how do robots support that. One of the things that we do know is that we are going to need robots to carry out a lot of activities when humans aren't present, because we can't keep humans in space indefinitely. And then even when humans are present, something I didn't talk about today is that we have to be able to use these robots to help support humans. On the space station, for example, right now exists because not only the people on board the space station, but the fact that we have a very large mission control team that's in continuous tight communications with the people on the space station. Well, think of what happens if you take those people and you put them far out at Mars, perhaps 20 to 40-minute round-trip communication delay, and they're no longer tightly coupled. Well, in those situations, when you need to take care of the vehicle, basic housekeeping and things like that, you're going to need robots to help support the humans that are trying to live and work there.
I guess you just I'm Morgan from Florida Tech. I guess you just sort of talked a little bit about that, but how do you see robots working in the future to build habitation for humans, and how do you see human and robotic teams working together from long distance environments?
Yeah, that's a great question. I think that if we are going to send people to live in some place, whether that's on the moon or Mars or other destinations, we have to find ways of building the infrastructure and maintaining it even when they're not present. And in particular, part of that is that we can't just launch every single thing that we need from Earth. It's incredibly difficult to launch large structures. It's incredibly difficult to supply all the information, all the infrastructure, and all the consumables that you need to continuously keep those things running. And so one of the things that we have to do is figure out how do we use robots for that? Are they just to assemble things? Do they support other things such as collecting resources and processing those resources? Ames, for example, is working on developing a future planetary mission called Resource Prospector, where we're interested in going to the moon and looking and characterizing the presence of hydrogen in the subsurface. And if we can really determine that, yes, this is a resource we can mine and then process, well, now we don't need to bring fuel along from Earth, or we don't need to bring water. We can actually mine it and use it on the moon. And of course, that's not something that we would rely on humans to do. We'd carry that out purely robotically. Those are the kinds of things I think are really important as we're looking towards the future.
Okay. So please join me in thanking Dr. Fong for an excellent seminar. Thank you very much.